yesterday's topics? Hello.
Not from my side, sir.
Okay, so some of the others, Pushpal, any query?
No, sir, it was fine.
Ganesh, M. Ganesh.
No, sir, it's fine.
Okay, okay. So just to tell you, I think, all of you should be able to use MATLAB online, right? I mean, I'm just asking.
Yes, sir.
Yes, sir.
Because institute license can be used online, right? So, and it is enabled so that you can use all of the MATLAB toolboxes. So in case you have not just checked, please check that, because it will be useful in our tutorials and also for future assignments and stuff. So fine. So we are done with a bit of scheduling theory, right? And what we'll now start doing is we'll cover a bit of dynamical systems and controller design, something which is kind of the theoretical foundation of cyber physical systems. To sum it up, when you are trying to design and analyze cyber physical systems, you need the following foundations: a bit of dynamical system theory and how to design, how to control dynamical processes, right? And then definitely you have the issue of real-time scheduling, because finally these controllers are going to be tasks running on RISC CPUs. So you have to understand a bit of real-time scheduling, which you have covered. And finally, we'll come to the issue of logic-based control design and synthesis, right? Like how this kind of controllers can be designed in two possible ways. One is using constraint solving problem, using the constraint solving approach of computation logic. And another is the more in thing now, which is the data driven or AI based approach. So that's how we are going to go through. And of course, we'll also talk about security aspects of CPS, which is very important nowadays. So fine. We now understand how the platforms work, what are the low power aspects of platforms, what are sensors, what are actuators, and finally how tasks can be scheduled and their real-time timing analysis be done on such platforms. So with this background of platforms that we have, let's delve into the modeling of dynamical systems. So pretty easy one actually. So what we'll do is we'll start with some examples of dynamical systems. Like I believe everybody in this class is familiar with a cruise control system, at least what it does. So as we know that if you just set, it can be like two kind of things. Suppose you are moving in an automobile and you can set a specific speed for that automobile, and then you can let go of the accelerator, and the vehicle will keep on moving at that set speed as much as it can, as long as there are no extra traffics coming and cutting on its way and stuff like that. And another possible way of cruising is you can set a vehicle in the front as a lead vehicle and make this vehicle, your one, the ego vehicle, to follow the lead vehicle. Okay. So there are several such cruise modes which you can activate in modern automobiles, and they are actually there in most of the automobiles that we have around us. Most of their top variants actually support such cruise control systems. Now, the issue is, why do we speak about cruise controls and stuff in the context of dynamical systems? Well, it's a dynamical system, right? Because it has a defined dynamics. Everybody is familiar with the concepts of dynamics and statics from your classical mechanics, right? So I can have a set of equations which captures the dynamics of a vehicle, the standard equations, right? Now, this is a very general concept, right? So for any continuous process that is occurring, be it the movement of a vehicle, be it the temperature control of a plant, be it a chemical reaction, you will have this kind of a set of differential equations which are essentially continuous time equations, and they dictate how certain process parameters are changing, right? So for any system for which you can control the dynamics or model them this kind of using this kind of continuous time differential equations is your kind of model of a dynamical system. So if you just try to build this kind of a model of a dynamical system for this kind of a vehicle, right? So you have the velocity and acceleration, right? Of course, one is the derivative of the other, right? Now, of course, the vehicle has got its internal mechanical power, and there is a resistive force BV, right, which is due to its rolling resistance and wind drag, and it's nothing. It's basically proportional to the velocity, right? So taking all these forces that are that are there, right, you can sum them up to using this standard Newton's law to generate an equation which is controlling the vehicle's movement, right? So you have the acceleration, you have the resistive force, and along with that you will have a net forward moving force, right? Now so if you just follow this, so this U is the net force, right? That is, I mean, it's simply representing the force generated at the road tire surface, right? So we can easily write this thing that, well, this is the overall forward acceleration, right? Now what it will be, it's nothing but U minus BV, because BV is the rolling resistance. So now you put BV on this side, and well, that's what you have, right? Now since I am interested in controlling the speed of the vehicle, so I can write another equation, I mean designating the speed as my overall output variable. So I can write another equation. So this Y is a standard. When we will be studying dynamical systems, we'll typically be using X for denoting variables, X as a variable or X as a matrix denoting a class of a vector of variables, right? For denoting all the quantities of the system which dictate the dynamics, or the fundamental quantities of the system which dictate the dynamics, and those we will be terming as a state variables, right? And there will be variables which provide me, I mean, quantities that I am really interested in. Okay. Now these variables on which I am really interested in their values are known as the output variables, and typically in dynamical systems we denote such variables using the Y. So the standard is X denotes the state variables and Y denotes the output or measurement variables. Similarly, for the motion of a DC motor speed control system, well, I can easily write the equations of motion for a DC motor, right? It's a rotary motion, right? And that gets translated to, if it's driving something, then that rotary motion will get translated to a translational motion, right? Like that. Now, the DC motor generates such kind of a torque which is proportional to the armature current, and the armature current, it's driven by an external circuit, right? And as we know, following standard rules of electromagnetic induction, the overall torque that is generated is nothing but proportional to this current and the magnetic field, right? So and accordingly a speed control can be done by controlling the armature current or the magnetic field. You can control each of these quantities to set the speed of the motor, right? So again, if you look at the basic circuit diagram of this kind of a motor, so you have this voltage that is applied. Now, of course, the motor has a moment of inertia, and it has a friction constant, right? There, and you can calculate the net torque that is applied using these electrical quantities that are there, right? And finally, you can set up the motor equations to calculate that, well, what is the rotational speed. So in that way, we will have a set system of equations. If we assume this magnetic field as constant, then we can say that, well, like we said earlier, the overall torque that is proportional to the armature current. Why? Because we are saying that in this motor system, we are not controlling the magnetic field. We are not controlling the magnetic field, but rather we are going to control this voltage source, and accordingly, we are controlling the armature current. Just asking, anybody in the class have, when I say armature current, Do you know what is the armature? Hello.
No, sir.
The coil,
Okay. Yes. Anybody from electrical or electronics? Hello.
so coil armature is coil that is
Yeah. So I don't know if you have ever, I mean, seen some mechanic uh, kind of maintaining fans at your place. So when they open up the fan, there is a coil where these wires are winded up, right? And and there is a surrounding magnet, and in that way you have this is the same principle. That is, you have the current rotating. I mean, this current moving through this coil, which is the armature coil, right? And it's surrounded by this magnet, and overall you have this electromagnetic induction principle that generates the rotational motion, right? But anyway, I am not going into that kind of details because of course we have a mixed background class and we don't really need that details, because this is just an example system. Finally, we will be operating in the abstraction of mathematics. But since, well, fundamentally we are engineers, so if somebody is interested, please look into, I mean, the basic operating principle of motors. I mean, it's a really interesting thing. I mean, I don't know, during our school days, there used to be a lot of magazines where they explained this, and that kind of aroused our interest in electrical sciences and engineering. It's an interesting thing. You can look into it. Coming back here, so what fundamentally happens is we have this electromagnetic induction principle generating the motor torque, right? And this motor torque is nothing but since it's proportional to both the magnetic field and the current. Now considering the magnetic field as constant, is proportional to the current, right? Now, similarly, when you have this kind of motor movement, there would be what they call as a back EMF. It's nothing but due to this movement, there is also a back EMF that is generated, and this back EMF is again proportional to the velocity. So when you have this motor moving, there are two forces in action. One is the electromagnetic induction force, which is generating this torque, and that is actually forcing this motor to move, right? Now, when the motor moves, there would be a resistive force generated due to what we call as back EMF, right? Again, I'm not going into what is back EMF and all that. Anybody interested, these are very standard things related to DC motors. You can just read them up. And I would say that, well, I mean, in our childhood days, a motor rotating was something of real interest. But maybe for you, the more pertinent example would be that of an electric vehicle, let's say a Tesla vehicle. All of them are moving fundamentally using these principles of DC motor speed systems, right? So, well, if you have an interest in autonomous vehicles, electric vehicles, if you want to explore them, I guess the starting point would be DC motor speed system, rather than the starting point being a neural network which is controlling the motion of the car. Unless you understand how the car operates, and if you just say that, well, it's all data driven, yes, it's data driven, but what is the data about? Questions for you. I mean that would really be a starting point. Well, coming back, so you have this kind of equation system which is dictating the forward torque on the motor. There is a resistive force generated by this back EMF, and as I said, it's proportional to the angular velocity. So the faster the motor is going to move due to the torque, there will also be this back EMF generated due to this movement. So as you can see, this B theta dot is operating in the reverse direction. So that means the resulting angular velocity would be dictated by these two opposing forces, right? So what you will really have is, I mean, this you will really have is this kind of set of equations, right? So you have this, as I said, ki, it's basically kti minus b theta dot, that is the back EMF, these two together is giving you the net torque, right? So that is J theta double dot. What is J, anybody? From your class 12 mechanics?
J is the moment of inertia.
Absolutely. So it's the moment of inertia of this motor head, right? So from that rotational mechanics equation, I can write J theta dot equal to Ki minus B theta dot, right? And so this is the equation coming from Newton's second law, right? So this is giving you the force equation. You also have a current equation. So you see two different paradigms are combining to give you equations for the overall mechanical system, right? So this second equation, can anybody explain this equation? So just look at this equation, L di dt plus resistance into current. So that's a voltage quantity V minus K theta dot. Now look into this circuit. Anybody?
It is voltage balancing in the loop.
Exactly. So you have this current loop, right? So this is the voltage, right? Now the amount of voltage drop in Ri. So essentially this is just evaluating Kirchhoff law, the current law across this loop, right? So voltage minus the voltage drop here R into I minus the voltage drop that would happen across the inductor. So that should be L di dt, right? And that should be equal to what? I mean, well, you have the, so these are the two voltage drops that are happening, right? So V minus these two voltage drops should equate with what? The back EMF value. And that's what we have. So V minus this K theta dot, there's a back EMF, must equate these two voltage drops. Fine. Any question?
No, sir.
So just asking people from non-E and EC background. Anybody here? Hello?
Sir, I'm in industrial.
Yeah, but this is clear to you, right? Hello?
Yes, sir. I
Yeah.
understood.
Anybody from a maths background in the class? I believe there were one or two. That's what I'm asking. Anyway, I think they are not present also. So fine. I mean, these are wonderful physical system examples. So from this, I mean, what we are trying to show is we have a dynamical system whose evolution is governed by this system of equations, right? So here we can give a formal definition now of a dynamical system. It's one which changes over time. And there are two possible kinds of dynamics, discrete dynamics and continuous dynamics. If the change is happening continuously at infinitesimally small possible time steps, then that's a continuous dynamical system. If the change is happening only at discrete time steps, then it's a discrete dynamical system. Okay. Now it comprises two things, like we said. One is the state vector. Now what is that? It's a minimum set of variables that fully describe the system. So what it means, see, if you have a set of variables, it will always happen that some of the variables depend on each other, right? So like we know that I can always have a minimum set of variables. If I know their values, then the other values are anyway going to be dependent on that. So this minimum set is what we call as the state variable set or state vector of a dynamical system. And there is a function which is going to tell me that, well, given the current state, what is going to be the change of the system? That means the rate of change function. So this function in a continuous time dynamical system would ideally be in the form mathematical in form of derivatives, which would really tell me that, well, given the current state vector, how the system is going to evolve. That means how each of the states in the system are going to continuously change. Okay. So if I have a state vector like this, okay, so mathematically we will start writing it like this, as we said that, well, x will typically represent the state vector and y will typically represent any measurable output quantity. Okay. So from the laws of physics, if we take an energy view of the system, it's told that, well, these are the state variables are the different variables which give a notion of independent energy storage of the system. And only when they together are all combined, you know the actual energy state of the system. Pardon the spelling mistake here. Okay. So if I have the full system of equations of the dynamical system, I have to try and bring them in a standard form. Why do I call it a standard form? So we should be able to identify for each of the state variables x1 up to xn, what are their individual rates of change. So we should write them in this form, so that I know what is x1 dot. That means how does it change with respect to all other variables? How does x2 change with respect to all other variables, right? When we write it like this, this is known as the state space form. We'll go into that later. Now we'll just give an example of what is a typical classification of dynamical systems. They can be linear or nonlinear. We'll understand what it means by a linear system. They can be autonomous or non-autonomous. That means they can be controlled by themselves, or they require a human or external intervention. So that makes them autonomous or non-autonomous. Now there is conservative or non-conservative. This is something we'll skip for now. And then we have discrete and continuous, like we said earlier. And of course, they can be one-dimensional or multi-dimensional. It's very simple. If there's one state variable, it's a one-dimensional system, and more than that, which is typically the case, so it's a multi-dimensional system. Now coming to linearity. So linearity means the system is linear if all the laws of superposition and they will hold, right? So if the respective state equations which describe the system, they satisfy these properties of addition and homogeneity, then we'll call them as linear systems. As we know that this is the standard linear equation, right? If x equal to y equal to mx plus c, so that's the standard linear form, right? So when you write y equal to mx plus c, we are assuming two things. One is the system is multiplicative, right? So you are assuming this homogeneity, that f of alpha y, f is the transformation, and we are trying to test whether this transformation f is linear or not. So we will say f as linear if f of some constant times the variable y is same as this constant times f directly applied on y, right? And then if f satisfies additivity, that means x plus y, then you apply f is same as you apply f individually on x and y and then add, right? So only when these both are satisfied, you have that form of line equation y mx plus c, right? Then so basically it's nothing but it's a combination of homogeneity and additivity. Now for all other cases where you don't have these conditions of additivity and homogeneity satisfied, we call them as nonlinear systems. For example, fx equal to x square. So any set of system equation where you have more than one state variable in a term, that means they are in a multiplicative manner, it's a non-linear system, simply because they will never satisfy additivity and homogeneity like this. Well, autonomous system is again easy to conceive of. It does not depend on any independent variable, and it doesn't need an external world operator. The system always knows from its current state where it will go by evaluating its set of differential equations. Now there is another thing which we call as time invariant. When do I call a system as time invariant? Well, when I am writing the system's equations, it may happen that the equation's parameters are also function of time. That means the system's nature, the equations that are guiding the system, they themselves are changing with time. If that happens, then the system is time variant. But if that is not the case, that means the system's guidance equations remain the same and only the variable values change with time, then we say that, well, it's a time invariant system. A specific class is linear time invariant or LTI system, so that if the system satisfies being linear and being time invariant, that's a very interesting class of systems which people study. So these are some examples which you can look into later. Now coming to this conservative and non-conservative systems. So conservative fundamentally means, well, there is no kind of energy loss happening in the system, okay? And the other is dissipative or non-conservative systems. Now that means where we bring in practical factors which are there always in systems like damping and friction. As we understand, the energy lost due to friction and damping, you cannot really recover and use it, right? So when we bring all these standard things, I mean the practical things together and then study the system, we'll call it a dissipative system, because the system for all practical purpose due to damping and friction is going to dissipate this energy. Now the next classification is discrete and continuous system. As we have said that the dynamical system can be continuous if we can write the system equations as functions of continuous time, where time is a real value. Now instead of time being a real value, if time starts becoming an integer value, that means we are defining discrete steps. Step 1, step 2, step n, these are integers, right? So if the system equations are written with time being abstracted like this kind of an integer, we call it a discrete system. That means the system's state cannot be evaluated in the continuous time domain. They can only be evaluated in the discrete integer time domain. Now, of course, we have already said what is a continuous time system, right? So you have the differential equations, and these differential equations can be evaluated in the continuous time, right? Whereas when we talk about discrete time, we don't have differential equations, but rather we will see that we have what we call as difference equations. Okay. Now, this class of one-dimensional and multi-dimensional systems, like we said, is simple. I mean, when they become vectors, you have multiple state variables, and we have these multi-dimensional systems. Okay. Now let's start and understand. Well, we understand how our dynamical system can be modeled using differential equations and what is their classification. That's fine. But then what is a control system? When we understand what is a dynamical system, we understand that, well, many of them, I mean, can be used to model engineering systems, and many of them, unless there is an external agent who is trying to manipulate the variables of the system, many of them would not be of any good use. For example, if I take the adaptive cruise controller, if there is not a piece of software which is correcting the errors that are happening over time, errors in the sense of measurement, errors in the sense of suddenly some vehicle coming in front and all that. So if there is not an external agent who is or who is continuously changing the parameters of the system over time, then this system doesn't really work, right? So this external agent is what we technically call as a controller, and the actual dynamical system whom this controller is supervising, we call it as a plant. Okay. So this idea of a controller and plant is quite generic, and it can be applicable to an electrical engineering system, to a biological system, information system, like that. So overall, the abstraction is like this. You have this kind of a physical system. It can be in different domains, engineering, biological, information, in any domain. You have outputs of the system. Outputs are the measurements, the variable y. The system state is given by the state vector, the vector x. You have disturbances which are kind of disturbing or perturbing the system, right? And you have control inputs who are guiding the system towards a desired output. Okay, so you have a desired output set, and the system is often getting deviated from a trajectory towards the desired output state due to these disturbances. And you have a specific agent who is giving specific inputs to the system, and these are known as control inputs, and the agent is called the controller, and only based on that the system is able to provide the desired outputs even in the presence of disturbances. So in this domain of the dynamical system and controller, a very important idea is that of feedback. Now we'll soon see that, well, feedback is something that is natural in a system. So if you remember the first time you have, let's say you have learned cycling, what did you really do, right? So you feel like, well, you are going to fall off on the left or the right, and accordingly you balanced yourself and you started to push forward, right? So the feedback is kind of this feeling that, well, my center of gravity is not really where I want it to be, and then I take a corrective action to take it back to the desired location, right? So this feeling that, well, it's deviating from its perfect position is what is kind of a sensory neuron feedback in the human body, right? Now when I go to an electrical system, I will have the feedback coming as measurements, electrical quantities. If it's a mechanical system, the feedback is coming in terms of transducers who are measuring the pressure or some other mechanical quantity, right? And based on this feedback is what the controller really operates. Does all systems have feedback? Not necessarily. We'll see. I mean, this is a very random example. So we are just showing two aerodynamical systems, a tornado and a Boeing, right? Definitely the aircraft is a control system. So it is, but what is similar among them? Well, both of them are dealing with wind equations in strict mathematical terms, right? But one is being controlled, so it's able to maneuver itself. The other is uncontrolled. So it's just that if you think of a cyclone or tornado, what it is just a set of dynamical equations. It's a plant without any controller. So the plant is unstable and is going to just move around and throw the wind unless and until the internal force completely dissipates, right? Completely dissipates due to the friction created, the wind resistance and all that, right? So fundamentally, I can think on the left side, I have a plant which is not controlled, and on the right hand side, I have a vehicle moving through, I mean, this uh, the fluid dynamical equations of the air, and but the good thing is it has got it maneuverable surfaces through which it is able to control its direction and speed of motion. So that's how we can define what a control system is. It's a process which causes the set of system variables to follow some desired value, like I have been saying earlier. Now, I mean, well, this is just another example of an automobile and all that. So what we can really say is, overall, when you think of, I mean, this kind of a system, what you really have is the plant. The plant's outputs are sensed. Based on the sensed output, in the feedback path, you have the controller who is generating a control input which passes through the actuator again to the plant, right? So in this case, the controller is controlling the acceleration. How? It is deciding the amount of fuel to be injected. So when you press the accelerator, it's increasing the amount of fuel injected into the engine, and according to the speed will increase or decrease, right? So this is a feedback controller in work inside a vehicle, right? Now, in general, what are the goals of controller design? Well, one goal is stability. Now, what is stability? It means you are trying to maintain the system at a desired operating point, right? Then you have the notion of performance. What is performance? Well, the system rapidly responds to changes. Sorry, the system responds to rapid changes. So stability simply means the system is trying to maintain the desired operating point. It's holding the steady speed. But performance means something different. You have to understand the difference between stability and performance. Performance means how quickly the system responds to a rapid change. So suppose the control input, which is the accelerator, changes for the system to a high value. How quickly will the car build up its speed, right? So that's practically the performance of a car, right? So when you see that people are rating fast cars, they typically rate based on the parameter that what is the amount of time taken by the car to attain a velocity from 0 to 100, right? Is it 9 seconds? It's 10 seconds. If it's not below 9 seconds, it's not a fast car, right? So how rapidly does the system adjust to this change or the perturbation is what we call as performance. But this is not stability. Stability will mean that, well, the system has been given a set point that, well, you start moving and you should maintain a speed of 60. Well, is the vehicle able to be at 60 after some point of time? That is stability. Well, how fast is the vehicle being able to reach 60? That is performance. The next thing is robustness. Now, let's understand the minute difference between performance and robustness. Performance means that, well, the system set point is changing and the system is trying to quickly react to that set point, right? Robustness means while the system is operating at a set point, there are errors, noise and other things which are creeping in. So the small disturbances or the noises, the system must reject the noise and try to be at the set point. So this issue of the system being able to reject the noise and being at the set point is robustness. The system being able to track the change of set point is performance, and the system being never driven outside its zone of operation is stability. Is this clear to everybody? This is very important in general. If you have a controlled, if you are from a control background, if you are from a non-controlled background but willing to study cyber physical systems, you need to understand this difference between stability, performance, and robustness. So, is this clear?
Yes, sir.
Okay. Any questions so far? Has this been under in a lucid manner, or are we going too fast?
No, sir, it's fine.
Now,
It's
once
fine,
we
sir.
once we understand well what is a controller and what are the metrics of a controller and all that, the next important thing is classification of control systems. A very basic classification is whether the system is an open loop system or a closed loop system. Open loop means simple examples, a light switch, gas oven, blah, blah, blah. Or let's say a more esoteric example, a missile launcher, a picture like this. So why do I call it an open loop? Simple, because I don't use any measurement from the plant to redesign my control input. I set a control input and accordingly this rocket is going to an angle and then I give the fire switch and it will just fire out, right? So that's the missile launcher system in open loop. Of course, I hope nobody is using this kind of a system. But a closed loop definitely would be something more, right? Like this, that well, I am giving the control command. Based on that, the missile is getting to an angle, but again, there may be errors in the perfect angle, right? So for measuring that, there would be a feedback path, and accordingly, this control command will iterate through this feedback path, and finally, this will be in the perfect position, and then I will decide whether to shoot the missile or not. So overall, this is like a general block diagram of a automatic control system, which you can find in any control theory book. So you have a process that is the plant. So this is kind of your set of dynamical equations of state, right? Now this these states, not all the states are observable. Not all the x values are observable. So we will always say that what is observable is y. Y is nothing but a function of x, and you cannot observe the x. If all the x values are observable, then we say that well, it's a fully observable system. Otherwise, it's not, right? So if you can observe this fx, that is the y, so that's your measurement, and those are sensed by the sensors, right? Now these values are fed back. Now you have a set point or a reference where these outputs are supposed to be, right? Now since there will always be some error, so there is a comparison between what is the reference point and what is the final measurement, and this error is what is going to the controller, right? Now based on this error, the controller is calculating a control signal, and that is passed on to the actuator, right? Now this actuator, its value along with external disturbances is what going to the plant or the process. So that's a very general diagram of an automatic control system. Of course, there will be many variants of it which we'll see. So this is the classical diagram, the analog diagram. But now when we talk about digital control implementation, what do you really have? So you have these actuators, the physical system equation, and the sensors, right? There are external disturbances, like I said. Now the sensor values, again, they can be affected by noise. There is what we call as process noise and measurement noise. Based on that, these noisy outputs go to the controller. Now this is again the output from the sensor. So the sensors measure values which are analog values. The sensor values come as output as digital values. So from here I get digital values, right? Sorry, so the sensors values are analog values. I measure a pressure or I measure a temperature. These are analog values. Now now these analog values need to be fed to the controller computer, right? But this computer is the digital machine, right? Now sorry, the sensors values are analog, they need to be converted to the digital signal, and then so we get the bit stream of sensed values. So this is the digital values. The controller software used in the computer will work on these digital values and it will compute a digital control output. Now this digital control output will be again converted to analog signals, and that's what will be again sent to the actuator. Now these are the points where external noise can disturb the system, right? It can disturb the plant, it can disturb the actuation values, and it can also disturb the sensed values. So you see there are several ways in which somebody is trying to throw your control system off balance. And that makes the job pretty hard, right? For an engineer, you have to tune your control system in such a way that in spite of all these pushes by the external noises, your system operates within margin of error, right? So that's what is the challenge of all control designers. And now with CPS and all that, what is happening is, well, you are doing the control design in software, you are communicating over internet connections, you are doing distributed control implementation. So essentially you have software controlling physical phenomenon across the globe in a distributed way. So whenever you have that, you have more external sources of noises, more external disturbances, right? Because you are simply increasing your number of control and actuation surfaces, more number of control and actuation surfaces, more places for people to attack, more places for environmental noise to creep in, and with all that, the control design problem for the cyber physical system becomes only complex, as we see later. There are again some examples which you can go through. Now we'll come to some more of representations. So like we said, we need to fix a method to study control systems, and for that we will study what we call the state space representation. So in the state space representation, we have some notion of input variable, output variable, and state variable. We have already said what is an output variable and what is a state variable. So variables that can be measured, variables of interest, they are my y or output variable. Variables, the minimum set which control the system's dynamics is the set of state variables, that's the x. And the input variable is what is the control input variable. That means the inputs or which control the actuator, which drive the system's evolution for the state variables. That is my control input variable. So this is again some repetition of state space and state variable. The fact that they need to be minimum in number, the fact that they need to be independent and all that. So with all those things, let's now come finally to the state space representation of a system. For a system of equations giving the dynamics of the system, what we will do if it's in continuous time, we will try to write it always in this kind of form. Consider this x as a vector, okay? Considering this x as a vector, we will try to write it in this form where on the left hand side we have the derivatives of x1, x2, x3 like that, and on the right hand side we have the x vector and the control input vector along with this matrices A, B. Similarly, for the output of the system, we like to write the output of the system as a function of again the state variables and the control input. This is in continuous time, and similarly using k we have it in the discrete time. So as you can see in the discrete time, we have the k plus 1th step system equation being derived using the measurements and values in the kth step, right? So in both cases, we can see that when we write them in this standard form, this is not the state space form, we get 4 matrices A, B, C, and D. Okay. So I think we have already discussed what is an LTI system earlier, and this is impulse response of the system. Well, let's keep it for now. Now coming to this, so like we have been saying that for LTI systems, essentially what do we mean? Like I defined that if it's a system is linear time invariant, that means the system parameters do not change with time. So whatever was this matrices A, B, C, and D, which we wrote as function of time, they will become time invariant, right? So that would simply mean the function, they are just constants a, b, c, and d, right? They are no more functions of time. So when it's linear time invariant, I can simply write it like this. Since it is linear, that means these ABCDs are not going to contain the state variables again, right? They are just going to be coefficients. Otherwise, it would be non-linear like we discussed earlier. So in that way, if the system is linear time invariant, and if we are writing the system's equation in this form, then it is guaranteed that here, when I write it, the ABCD are just coefficient matrices of the system. Okay. So fine, then what we will do is we'll stop here, and maybe in the next lecture we will start with some examples of, given a set of dynamical equations, how to derive the ABCD matrices and all that. So what I will ask you to do is, for tomorrow's lecture when you come, there is something which I have not yet covered, but I will ask you to read this and come to the class as much as you understand. From here we'll start our discussion. Doga Shiva, you are not, yeah, fine, thank you. So is this clear? What I am asking you to do is, please read this time response analysis part and then come for tomorrow's lecture. Is that fine? I think it should be doable, because I believe all of you have studied Laplace transform in first year engineering math. Am I correct?
Yes, sir.
So with your background of Laplace transform, you should be able to read this last subsection in this slide, and so that we can have a more fruitful discussion tomorrow. Okay.
Yes, sir.
I mean, of course, I am not asking you that you will understand everything that is here. Whatever you can. Not everything should be understood by you. Okay. So with this, we'll stop today.
Thank you, sir.
Thank you.
Thank you, sir.
Okay. Bye.
Thank you, sir.
Thank you, sir.